I was going to say okay then, but I've managed to stop myself, although I just now said okay. Right, bubble sort. Bubble sort, the lowest of the low when it comes to, well, it's not the lowest of the low. The lowest of the low is selection sort. Okay? So, just to give it some context, and in general, and the exam board will maybe expect you to say this, we're talking about key values, like I said, referencing to some structure where we've got records of data. So we shouldn't really get duplicates of these numbers or whatever the values are that we're searching for. Okay. They sometimes use names, alphabetical names, but there has been hilarious mistakes in the past with exam questions that had names in, where they've written the question wrong and they couldn't get the alphabetical order right.
So is this bubble sort you're going for first?
You what?
This is bubble sort.
I'm going to go for a bubble sort first, yeah. Okay, right, bubble sort. It's quite a nice simple thing. The actual premise of it is that the swapping action that we're going to do, and all sort methods generally require some sort of swap mechanism. The swapping we do, we keep doing until we don't have to do any more swapping. It's pretty dumb, to be honest. It assumes nothing about the data, apart from one little thing. So what we do is we look at pairs of data items. And we say, let's assume we're going in ascending order. And all bubble sort does, because it's only looking at two things at a time, it just compares two items and says, are they in the right order? That's all it does. And that is the whole, that's it, that's the algorithm. Are a pair of items in the correct order? And we look at this and we go, they're in the correct order, leave them alone. Leave them alone, stop hassling them. Then we look at the next pair of data items. And we look at them and say, they're not in the right order, so we have to swap them. Okay? Tricky to do. The exam board, when they ask you to show how something's sorted, what they'll want you to do is to write it out and show that they have swapped like that. So do row at a time for every time you do a swap. I've lost my ball rubber. But I'm gonna rub them out because I've got a massive whiteboard. So I'm gonna swap those two values around. And I move on to the next pair. So the next pair is there. They're not in the right order, so they're going to get swapped. Now the key thing is that I have done a swap. Look at the next pair. Notice I don't recheck a pair that I've just swapped because that would be stupid. They're in the right order, so I'm going to leave them. Then I do the final pair, and they're not in the right order, so they need to swap. So we've gone through there once, so we've done one pass. Done a few swaps, but you can see it is not in order. Okay? Now, what has happened though is that the biggest number is now sat at the end at the right place. So we don't actually need to look at that location again. No point. Nothing's going to be bigger than it because it would have been at the end itself. So the next time through, we only have to go one item less. So you can do, there's a little bit of efficiency you can do. I have seen implementations of this algorithm where they always go to the end, which is a bit mad, really. But there you go. So we just go through the whole process again. So we look at a pair, I'm going to draw arrows now instead of big boxes. So I look at those two, they need swapping. So I swap. Look at the next two, they need swapping. Look at the next two, they're fine. Look at the next two. They're not. They need to swap. I don't need to look at the last ones because that's already in place. So I've done a second pass. The worst case scenario with bubble sort is reverse order data. If the data that you're sorting is in exactly the opposite order, every single time you look at a pair of numbers, you're going to swap. Every time down the list, every pair of numbers will have to swap. That's the worst case scenario. So it's pretty tragic. But it is quite efficient if you've got a partially sorted set of data. And whenever you're selecting algorithms for doing jobs, you really need to understand what your data sets look like. Because you can have outcomes from processing that give you partially sorted data. Or you might have situations where you've got reverse order data, so you want to know what algorithms to avoid. So it's important to understand what you're doing. So again, that one's locked in position. So we've reduced. It actually looks like it's in order, but the computer can't know that because we did some swapping. Okay, so we start again. So we look at this pair. They're okay. Look at this pair. They're okay. Look at this pair, the last pair. They're okay. I didn't do any swaps during that pass through the data. That's our stop condition for bubble sort. If I didn't have to perform a swap, then they must be in order. Okay. Again, I tended to knock this up if I wanted a quick sort routine. Of all the sort routines, other than selection sort, which just says find the smallest number, put it in a new list, it's relatively simple to knock up. Even in assembly language, it's easy to knock up. There is actually, on that Little Man computer emulator, that web one, there is a bubble sort example, but bubble sort on Little Man computer is not easy because you've got to use self-modifying code because it's only got that stupid direct addressing mode, but there you go. Right, okay, so that's bubble sort. So that's the simplest of the sorts we look at. The next one is insertion sort, which tries to use something about the data. So it's got a premise. So let's do some more numbers. 4, that'll do. Right, the way that insertion sort works is it starts at the second item in the list. Okay, and it makes an assumption, and what we do is we walk that way through the data. So we pass along the data once, but we do some looking back. Okay, for an insertion point. So what we do is we assume, and a lot of sorting algorithms make this same assumption, that if you've got one item of data in a list, it is automatically sorted because one item on its own must be sorted. No matter what that number is, it's sorted. So if you look at this part of the list, 5 is sorted. Okay? So insertion sort says, okay, let's start with the second item and let's just keep a capture of that because we're going to start shuffling. And we call it a key. The key, the thing we're trying to place. So what we do is we look back in the list to the left, which we know is sorted. Remember, one item on its own is sorted. And we see if we need to shuffle data around. So we look at the previous list and we say, okay, 5 is bigger than 1. So what we're going to do is we're going to move the 5 across. Okay, we looked at the 5, we're going to move the 5 across, and then we're going to decrease our pointer. If we fall off the start of the list, we've found the insertion point. Okay, it is one place to the right. So we put our 1 in there. And then what we do is we move on and we say, okay, we're going to now say that this part of the list is sorted. And you can see that that is sorted, 1 and 5, they're in the same order. So we go for the 7 next. So we say our new key value is 7. So let's look back to the left-hand list that we know is sorted. The biggest item should be the first thing we see. So we compare that and we say, actually, 7's in the right place. It's bigger than everything in that list. So it can stay where it is. So we don't have to actually do anything. We did one comparison there. So we move on and grab the next key value, 9, and we compare it. So again, this is the left-hand list, which is now sorted, 157. And we compare with the item at the right of that list. And we say, okay, 9's bigger than that, so that's sorted. So we haven't done much work yet. Now we'll get something a bit more interesting. So we look at the next number. We've only got 2 more to look at for placement. So we say, right, our next key is 2. Let's move through that left-hand list, which you can see 1579 is sorted. And we say, okay, is the key smaller than the item there? Oh, yes it is. So let's move it along to leave the space. Okay, so we move the 9 along. I don't rub things out. Remember, we don't ever set something to 0. We just overwrite things. Okay, so we step back. This is why it's called insertion sort. We're moving things away so we can put something in. We're making it, it's like a sliding block puzzle. That sort again, where you're moving a hole around. Literally, you're moving a hole around without, you can't touch a hole, but you're moving blocks out to move the hole. So it's that same sort of process. Right, so we look at the 7, we say, oh, we're smaller than that, so we should be to the left of that, so let's move the 7 along. And we'll move back through this list. So we're going back through this list to find our insertion point. Compare it with the 5. Okay, oh, it's smaller than that, let's move the 5 along. This is its downside, it's a shuffle that we're doing. We then move to the first item in the list, but 2 is bigger than that. So we found our insertion point. So our insertion point is to the right of where we were just looking. So we can put our 2 there. Okay. So we've now processed all but one data item, and this left-hand list is all sorted. This sort method comes about from the way people sort decks of cards. So it's actually based on how humans sort things. Right, so we're then going to look at the last item that we want to put in as a key. So 4, and we go through the same process. We start looking back through this sorted list, moving things to the right if they're bigger. So 4, 9's bigger, so let's move the 9 across. And the reason we have to take a copy of the value we're inserting is because I've just obliterated it. Okay, I've had to take a copy for that reason. So I move back, look at the 7, 7's bigger, so let's shift that out of the way. Look back, 5's bigger, so let's shift that out of the way. Look back, 2 isn't bigger, so we found our insertion point. Okay, so 1 position to the right of where we just looked, we're going to put our key, and it's sorted. It's a little bit more complicated to implement than bubble sort. Bubble sort is pretty straightforward. But it is really, your insertion point is either you've got a negative number, so this wouldn't work in Python very easily, a negative number for your index that you want to search. You say, oh, it must be inserted at the start. Okay? Every other time, so you just say -1. If you add 1 to that, what do you get? 0, which is the first position in the list. So it actually nicely works. We just add 1 to the last search position, and that gives us the insert point. Okay. Insertion point is really quick if you've got partially sorted data. Okay.
Eric, you have to go to it.
Yes, that's on camera. Sean. Right, I'll start that one then before I do the more complicated one.